Hello everyone, I am Jerome Govenden, and together with Jan Gehl here, we will be presenting our SoK paper on the efficient design and implementation of polynomial hash functions over prime fields. This is a joint work with Jean-Paul de Gabriel and Kenny Patterson. In this talk, we will explain how we have designed better polynomial hash functions by doing a systematic exploration of the design and implementation aspects. I will start by giving some background on Poly 1305 and our SoK. Then Jan will describe our benchmarking framework and our new designs. As introduction, the security notion satisfied by a polynomial hash is what we call delta universality, meaning that given the value z, it is hard to find two distinct messages mm' for which the difference between two evaluations of the hash function h is equal to z. It has multiple practical applications, such as in data structures, in message authentication codes, and AED. SoK20 Poly 1305 is notably a popular AED scheme based on Poly 1305. In more details, its two underlying primitives were first independently designed by Bernstein, and then later combined in 2013 in an ITF draft. Simultaneously, it was immediately supported in Chrome and OpenSSH. 2 years later, the draft is finalized in RFC 7539, and in 2016, SoK is selected for usage in TLS and as default choice in OpenSSH and WireGuard. From there, it is then adopted in other applications, such as in OTRv4 and the Bitcoin Lightning Network. So as key points, we can note that SoK has good performance across all architectures, without the need for any specific hardware support, such as the AES instruction or carryless multiplication. Moreover, it is also often seen as a backup algorithm to the very popular AES GCM scheme, and thus can be used as fallback in the event that a vulnerability is found in AES. But more interestingly, as shown in the timeline, it was quickly adopted, even though AES GCM was already a predominant scheme. And this is due to its conservative and simple design, which is focused on performance while providing only standard AED security. And in this talk, we'll focus more on Poly 1305. So Poly 1305 is a keyed hash function, which takes as input a key R and a message M. The message M is split into blocks, and each block is padded with a 1 bit to form a coefficient Ci. For the 1 to 8-bit key R, 22 of its bits are set to 0, which is a procedure called clamping. Poly 1305 is then the evaluation of the polynomial in X with the coefficient Ci reduced modulo 2 to the 130 minus 5. The final result is then reduced again modulo 2 to the 128. So this is quite an efficient design, but it also has some limitations. Firstly, while clamping was introduced for fast implementations using floating point units, most implementations today don't benefit from it, as they use integer ALUs instructions. Secondly, this clamping reduces the security to 103 bits, while 128-bit would have been expected due to the size of the key and the tag. And the limitation is that Poly 1305 is tailored for 32-bit architectures and not for 64-bit ones. And finally, in an analysis by de Gabriel et al., it was showed that SoK has limited multi-user security. And this is due to the Poly 1305 part. So with all these limitations and the apparent disconnect between Poly 1305 and modern hardware, there's a legitimate question to ask that, given today's advancements and applications, would we still converge to the same design? In attempting to answer this question, we took a look at the current standpoint and noticed that there was a broad design space with multiple interactions between the different choices, and that the knowledge was spread across a variety of sources. There was therefore a need for a systematization of knowledge. Thus, we have gathered and organized this knowledge, and we have classified them into design choices that are fixed during the specification, and implementation choices that are left to the implementers. There's a complex interplay between these choices, which our exposition aims to clarify. The design choices limit which implementation choices are available to implementers, while conversely, a designer should be informed on the implementation choices and performance allowed by its design. To now give a brief overview of this design space, usually start with 2 bit strings representing the key and the message. These are needs to be encoded into field elements, and behind this seemingly simple encoding hides already a wide variety of choices. For instance, you need to decide which block size to use to split the message M while keeping memory-aligned data that allows fast memory access. This also needs to not decrease the security of the construction and be compatible with the field chosen. Then you can combine securely the key and the message through a polynomial. And among the choices of polynomials, one example could be the classical polynomial, as the one used in Poly 1305, where the message block are multiplied by a power of the key. This allows a certain number of polynomial evaluation strategies, such as Horner and autovariance. Then, once evaluated, you obtain a tag T, which is the field element, and this needs to be encoded again securely and efficiently into a bit string. Now that we have an overview of this design space, I will delve into only one specific aspect to give a glimpse of the complexity of this design space. And this is field multiplication, which plays a central role in polynomial evaluation. So in a machine, field elements are stored into words, which depend on the size W of the architecture. Each word is also called a lim, and in a saturated representation, all limbs are filled to the maximum, except the last one. For the size of field we consider, schoolbook multiplication tends to be the most efficient algorithm. As example here with 3 limbs, usually start by multiplying the 2 rightmost limbs, then the middle and the right one, then the left and the right one, and then you would continue until you have multiplied all the limbs. A problem that arises, however, is when you want to sum all the rows. In the second rightmost column, as the 2 terms are fully saturated, it is impossible to sum them without first doing a lim realignment. And so a solution to this problem is key clamping, as done in Poly 1305, where for the key R, you set the highest bits of each limb to 0. This reduces security, but then avoids the previous problem. However, a big limitation is that it's not exploitable in several polynomial evaluation algorithms. Therefore, the more generally adopted approach is the unsaturated representation, where the data of each field element are distributed as equally as possible among the limbs. And now I'm going to hand over to Jan, who will describe our benchmarking framework and our new designs.
We've seen so far that when we want to design polynomial hash functions, we have a huge design space to deal with. And that leaves us with a bit of a problem. Namely, how do we pick a concrete design from this huge space? This is difficult because we have to understand all the different combinations of options we have and how they interact with each other. And we have to be able to test this empirically because these interactions might differ on different hardware in ways that we can't easily theoretically predict. So how do we solve these problems? Well, we just reuse the modularization that we did for our systematizations and define our hash functions as modular configurations. And then we use these modular configurations to use high-level C implementations and auto-generated code for performance-critical parts to automatically generate these implementations instead of writing them by hand. Now, in a bit more detail, we have our benchmarking framework, and we take our configuration files as input, parse them, feed them into our arithmetic generator, generate our field arithmetic, glue this together with the polynomial implementations, the encoding, the high-level hash function interface, as well as our benchmarking harness, and then run this through a normal C compiler, and we get our hash function library, which we run a battery of fuzz tests against, and get a benchmark executable, which we run and then plot the results in a nice graph. So we have a tool. How do we explore this space? What are our goals? What do we want to achieve with our new designs? Well, we want to be more efficient than Poly 1305 in the sense of a runtime security trade-off. We also want our designs to be simple and familiar to developers so that they hopefully can find fast adoption. Furthermore, we want our designs to allow for various optimization strategies so that implementers can really tune their implementation to the exact hardware they're running on. But we want to achieve all this without actually tailoring towards a specific implementation strategy or specific hardware. And concretely, we don't want to design for FPUs. So, our new designs, well, as already said, we don't want to support FPU implementation, so there's no clamping in our new designs. We don't think this is worth the security loss. Furthermore, we stick with the classical polynomial over FP, and we're trying to pack the limbs as full as we can. Our designs all allow for delayed reduction strategies as well as two-level polynomial evaluation strategies, and this should really enable implementers to fully exploit the parallelism in their CPU. Now, in this work, we've come up with 5 new designs targeting 3 different security performance trade-off levels: high performance at Polythorium 5 security level, higher security at Polythorium 5's performance level, and one very high security level which sacrifices performance. Now, I said 5 new designs for 3 categories. Well, for the first 2 categories, we actually have 2 designs each. One that's aimed only at 64-bit architectures and one that's aiming at both 32 and 64-bit architectures at the same time. Whereas our very high security design only targets 64-bit architectures. Okay, so for our targets, well, if we want to design a hash function, the first thing we need to fix is a prime field. So do we have suitable primes? Yes, we do have several suitable primes in this range. And choosing these primes, we can actually fill up our limbs quite nicely. And for each of our categories, we are actually able to hit our security target. In the first one, we are slightly above Polythorium 5 security level, whereas in the higher security at Polythorium 5 performance, we are between 30 to 50 bits higher than Polythorium 5, whereas in the very high security scenario, we are more than double the security level of Polythorium 5. So this leaves us with these 5 hash functions: poly 1163, 1223, 1503, 1743, and 2663. Again, not all of these are suitable for all architectures. Here, only 1163 and 1503 are suitable for both 32 and 64-bit architectures. The remaining only support 64-bit well. Of course, they run, but likely at worse performance. Now, I said we have a benchmarking framework, and that is what we did. We benchmarked these implementations after generating them. And here you can see these 5 new designs together with Poly 1305 as generated by our framework, and as another reference, the OpenSSL implementation of Poly 1305, which utilizes AVX too. And with the exception of 2663, which is performance-wise quite an outlier, all of our hash functions, our new designs, lie neatly in between our generated 1305 and OpenSSL 1305, but without using any vectorizations. Specifically, 1163 really achieves quite nice performance, where we're very close to vectorized 1305, and for smaller messages, like around 7 kilobyte or less, we actually outperform Poly 1305 in OpenSSL. Now, let's look at 1163 and 1503 in more detail across several CPUs, because this previous graph was only one CPU. Again, we have OpenSSL's Poly 1305 and our generated Poly 1305 as a kind of reference. And together with the previous graph, we really see our implementations already, without any vectorization or hand optimization, achieve high performance. Furthermore, if we look at the Core i7-940 here, this is an old CPU and doesn't support AVX, and so OpenSSL just falls back to an integer implementation, same as we do. And here we see actually, well, our polytheorem 5 is quite competitive with OpenSSL's polytheorem 5, and 1503 outperforms it slightly, and Poly 1163 just massively outperforms it. And this kind of already shows that Poly 1163's performance already makes it a suitable drop-in replacement for polytheorem 5, especially on some CPUs, for example the AMD EPYC here, where we actually outperform vectorized polytheorem 5 for messages up to 16 kilobyte. Now, I've said vectorized a lot. We haven't vectorized our implementations, but we have some expectations for what would happen if we do. So for one, we would expect that 1163 gets significant performance boosts, and to the point where we should massively outperform polytheorem 5 at the same security level. And Poly 1503 should be able to reach similar performance as polytheorem 5, but with an additional 34 bits of extra security, which would make it a very good replacement for polytheorem 5. And with this, I conclude our talk. Thank you.